So finally, I'd just like to introduce Professor Runming Yao, who will chair the next session. She is a professor of, from Reading University and director of the design and management of sustainable built environments. So over to you, Runming.
Thank you, Chris. Thank you very much. I'm very delighted to chair this session, session 4. In this session, we have 4 speakers. I'm a little bit worried about concerned about the time. It's slightly behind the scheduled program. So I would like our speakers to all keep the speak within the 20 minutes, including question and answers. So I'm very happy to introduce the first speaker, Sumanas Sarma. Sumanas Sarma finished his graduate studies at Queen Mary University of London, in which he specialized in advanced analytics, software verification, and machine learning. He has industry experience in retail and productionization. He worked at Sainsburys before his current role as the principal machine learning engineer at Infosys Consulting. His talk is on the title is Simulating Human Interactions in Supermarkets to Measure the Risk of COVID-19 Contagion at Scale. So it's over to you, Sumanas. Thank you.
Thanks. Hi, I'm Sumanas, and I'm here to talk about how at Sainsburys we simulated human interactions to try and measure the risk of COVID-19. So what I'm about to present is the joint work of the 5 of us, Serge, Melvin, Christine, Dave, and myself. We also had funding and support from Google Cloud, which allowed us to run our simulations on their platform. So a massive thanks to them. I'd also like to point out that I'm no longer working at Sainsbury's, so I can't comment on the current measures that they're taking. And finally, for what it's worth, I recently had COVID, and according to NHS Test and Trace, it's almost certain that I got it at my local Sainsbury's. So I hope that gives you the right perspective going into the talk. So what we wanted to do was find an optimal set of policies for each store that we have that would minimize the risk of infection. And a policy is something we're defining here as a store-specific configuration. So we're not going to have more than 50 people in the store, one-way aisles, dividers, things like that. And Sainsbury's has close to 1,000 store locations, and each of them have their own tailored layout, specific geometries, things like that. There are common elements, of course, the checkout tills, the location in proportion to the entrances and exits, but largely speaking, the aisles and stuff are set up based on the location where the store is. We have data on the location of the items within each store from the floor plans. And the plan was, while we're running these simulations, is it possible to learn which policies tend to work better than others? And can this framework that we are building be used in the future, or is it something that's only specific to this pandemic? I think some people have figured out by now I'm talking about agent-based modeling. And we ran our simulations in Unity, the Unity 3D game engine. There were a couple of reasons for this. It has a good physics engine built into it. It has the ability to import meshes, which was very important for us because we needed to construct all the different store layouts in 3D from the floor plans. And finally, it allowed us to run it in headless mode, which is we were running it in the cloud in parallels, which meant that we didn't have to sit and watch the simulations as they took place. So we were collecting the data from these millions of simulations. To give you an idea, if you have 1,000 stores and you need to run 100 simulations per store, that's 100,000 simulations just for validating a particular set of policies. So with GCP, we were able to scale this out quite easily. We used BigQuery to store the individual results. So the result of each simulation was stored in here for analysis. And we needed the ability to audit and investigate what happened in a specific simulation. So that was done by storing in a time series database called InfluxDB. So each of those million simulations, we were storing every few seconds what the location of the agents was, and that was then being recorded in this database. So if we needed to investigate what happened, something looked anomalous in a specific simulation, we can just pull that down and view on Unity Editor what's going on. A simulation here we're specifically defining as covering the entry and exit of customers to a store, specific store on a specific day of the week from open to close. And an experiment was made up of n such simulations along with relevant metadata. So n was determined based on how many people had visited the store. So it's historical activity looking back over the last 5 years on that day of the week. When it came to modeling the contagion, so at the time, April, May last year, there was considerable uncertainty regarding the specifics of the transmission. So the general idea was being close is not a good idea, keep your distance. And there were different official definitions of what close was. And we heard yesterday how the WHO got some of it wrong right at the start with the airborne transmissions. So instead of focusing on the spread, we said, let's use collisions. And we're defining collision here as something as two people within the store coming within a certain radius of each other. So it's not a physical collision. It's just if you imagine a 2 meters sphere of 2 meter radius surrounding a person, would those spheres collide? And we could then control what was happening, control the radius of that and see what the effect of different social distancing measures would have. So cumulative exposure is what we were then measuring, where the exposure being a collision that lasted at least a second. And this allowed us to say, we want to now optimize for a lower average exposure per agent. This is what a typical simulation looks like. So this is a screenshot. We have a spawn point, store, despawn point, and the agents. So the agents are spawned into the environment based on the time of the day. So we know between 8 and 9 what was bought at that store historically. And using that data, we can give a shopping list to these agents. I'll come to in a bit how that was determined. The agents have partial knowledge about the location of items within the store, and they make their way through the store, looking at picking up the items, visiting these bays. Then they go to queue, go to checkout, and head out to the despawn point. The store here is constructed purely from the floor plans. And again, I'll come to towards the end how we did that. But essentially, this is not a handmade 3D model. We just created the individual meshes, and then we used the floor plans to construct the layout of the store. The collisions themselves are measured using the Unity physics engine, which is pretty good for rigid body dynamics. And it gave us the ability to execute these distance queries. So on the right-hand side, you can see these agents are measuring the distances between each other. That's the lines in red. And you'll notice that on the top left and the bottom right, the agents are not measuring. There's no red line connecting them. That's because we have this idea of an observation radius. So anything that's outside that observation radius is not being counted. And that's how we managed to keep the computation complexity within limits. Otherwise, if it's always measuring with everyone else, it would just become too difficult. What we got for free, which we weren't planning on using, but we kind of got it as a side effect of using this engine, was the surface normal. So in green, you can see these lines extending. So this is telling us the direction in which the agent is pointing. So this is particularly important if you want to start adding in masks and coughing and sneezing. This would allow us to basically then say, we know on all the simulations, what orientation the agents had. The different behaviors that the agents were coded with was trying to mimic reality. So the idea was, would it be possible to build a baseline? So let's model pre-pandemic shopping behavior, and then let's layer on something like limiting 50 people max in the store. How does that affect the average exposure per agent? Is that going to slow down the rate at which people shop? Is our queues going to build up outside? Things like that. So the agents will move at different speeds. They'll get slower as they start adding items. They wander through the store, and there's a long list of these things in our paper. I'd like to specifically call out two things. So first is this Wander AI. So this is the idea that when the agent is spawned, they're given partial knowledge about where items are located in the store. So they used a Poisson distribution for this, and we said, well, when the agent comes in, let's say they've got to get milk, eggs, and say hot sauce. So they know where the milk is, they know where the eggs are, but they have a rough idea which bay it is, which aisle it is, sorry, or it's towards the back of the store, things like that. And that allowed us to have the agents wander around the store trying to find the items. Second thing is an impatience counter. So whilst the agent is moving around, everything is fine, but as they encounter unnecessary delays, maybe there's a blockage, maybe there's a small, because of social distancing, you have to wait while people are moving past you. So these things add up, and as this, as the counter crosses a certain threshold during the length of the run, the agent will give up being patient and will basically just try to cut across. So for example, during the one-way aisles experiment, we found this happening a lot. A typical flow of what it was looking like when we were running these ones was we would select a store on a day of the week. We would choose which policies we wanted to test. We would trigger our scheduler to execute them. And so this is now running in the cloud. It's running in headless mode. So we have to monitor via a dashboard in Google Cloud what is happening behind the scenes. And a notification gets sent to us saying, okay, you finished your 100,000 runs or whatever it was that was needed. The experiments are then analyzed. We pull the data out of BigQuery, we perform an analysis, and one of the key outputs was a hotspots, which is like a heat map laid out on top of the store. So we could say, all right, as a baseline, this is what it looks like. These are the hotspots of the store. But now we introduce these, we close off this bay or we close off this aisle, and let's see what happens, things like that. A key part of any of these simulations is to ensure that we are not straying too far from reality. So calibrating how these simulations were, I would say, mimicking or trying to mimic what happens in the real world was key. So this is an idea that my colleague Serge had, which was to try and map the customer trajectories onto a torus for collision detection. So loosely speaking, if you look at a floor plan from a top down as a piece of paper, you have your path or the trajectory that a customer might take as they're going through the store. As there's 4 line segments up here, they're sort of moving along and trying to find what they're looking for. The idea being, if we want to say in an ideal world at t equals 0, as customer enters the store and they go about their shopping list, at t equals 1, another customer enters. So they're entering one at a time. And can we mathematically determine when of 2 of these paths are going to intersect and they're going to come across each other and the collision is going to happen? If we can do that, then we can simulate that in Unity and ensure that in this highly toy and idealized world, if our simulations are matching up what we're seeing from the mathematical formulation, then we're on the right track. So over here, you take the plan, you sort of curve the edges together to form a cylinder, and now that those disconnected line segments are looking like a curve, but the tops of the cylinder are still disconnected. So if you connect those up, and now you get your torus, and now you end up with a continuous curve that we can run our intersection calculations on. After this, we needed a second form just as a safety check, which was a Wi-Fi mapping. So this is, in certain stores have Wi-Fi hotspots. As a customer's moving around the store, their smartphone is constantly pinging these routers to try and connect to the one that's nearest to it. So this gives you an idea of, as people are moving around the store, what's happening. This is not in all the stores, it's only in a small subset, but it allowed us to get a second form of verification that the hotspots that we were generating from our runs was having a semblance of reality compared to something like this. And I should point out, this is of course anonymized, so we're not actually seeing any real customer data. The scale at running the simulations, so we had this idea that the experiments would encapsulate the policies that we wanted to test, and say we needed to run, in this toy example, 6 simulations along with a store and a day of the week. So that would be distributed by the job scheduler across 2 jobs, and that would run in parallel. So the key thing is here, these are all running at the same time. If for example, something goes wrong, sometimes an agent might get stuck in the geometry, or maybe it wasn't constructed properly, and so there's a timeout. So we store that, we flag it that maybe we need to look at that as an error, and we rerun. So that's the responsibility of the job scheduler to say, well, we need to rerun that simulation to see if it can run through. And if it keeps failing, then it flags it up, sends us an alert, and we can investigate. I'm not going to delve too much into this, but loosely speaking, we had an auto-scaling cluster. Again, thanks to Google Cloud, we were able to move up and down. So as some days we were running loads of simulations, some of them very few. So that was allowing us to grow and shrink the cluster as needs dictated. The store geometries, I think, is an interesting problem. So how did we go from floor plans to the 3D layouts? So on the left-hand side, we have a CSV. So this is coming from the floor plan. What are the different objects? You have the entrance, the exit, the shelves, slanted shelves, stands, refrigerators, checkout tills. So this is a fictitious store that I've used here. And we've got the location, the coordinates within the store, along with the dimensions and the orientations. We've constructed on the right-hand side 3D meshes for each of these, I would call it units. And then when we process this CSV data set, we can then produce this map on the right-hand side, which is the store in 3D, ready for our agents to go in and run their calculations. The key thing here is that this is not specific to supermarkets. If you have your store geometry, if you're any geometry available for a station or for any building available in this format, this is applicable. It's not just something specific to Sainsburys. The shopping lists, we wanted to have the shopping behavior as close as possible to what people were doing, but we didn't want to go in and going through personal shopping. We didn't want to have to go through the shopping data. So the idea being, let's try and mimic the distribution that we normally see. So this is a small simulation that, animation that I made to try and explain how we gave our agents shopping baskets that mimicked what happened in reality. So you want to have a list of items that were sold between 9 and 10 a.m. and you want to randomly choose. So we have 10 apples that were sold and 6 bananas. Then you convert them to the fractional equivalents. That tells you that this is what was sold. You map those counts to values between 0 and 1. The purpose of this is now when you draw numbers from a random uniform distribution, you can check the value to see if it's less than 0.625, then that's an apple that the agent has to buy. And if it's greater, then it's a banana. So in this way, we cared about what was bought, not who bought it, if that makes sense. Specifically, what was out of scope was airflow. We didn't have the capability to handle ventilation. Agents wearing masks, again, because of the issues with the ventilation simulations, we didn't really get around to doing that. We assumed that all the agents were asymptomatic, so an agent who's deliberately coming and coughing was not modeled. Queuing outside the store is a bit interesting. I'll come to that in the next slide. I'm almost done. And the public areas of the store were modeled in the first iteration. So the staff areas at the back, if the store is in a mall, what's happening right outside was also not a part of this run. Replenishment of stock. So during the day, as stock goes up and down, colleagues would have to go in and replenish it. So we were able to provide some feedback on what are good times to do the replenishment, because the simulations would show us that this is the sort of activity you can get. But beyond that, that was left for next iteration. And finally, the training of the graph neural network, that didn't really happen. We ran out of time to complete this, but that would have been nice to do. Partial results. So again, these experimental results is not an indication of what actually Sainsbury's ended up implementing on the ground. That was a different part of the business taking care of this. So grouping commonly bought items in an easily accessible area, we noticed wasn't always a good idea. So, okay, there was this plan that let's see if in the simulations we can put the 10 most commonly bought items between 9 and 12 right at the front of the store, so people come in, pick them up and leave as quickly as possible. But then that just, in a small store, that just creates a center for people to come in, jostle for picking up items, and it's not really working out in practice. One-way systems not really used anymore, but at the time, there was a lot of debate on should they be a good idea or not. What we found was that basically they're triggering the impatience threshold frequently, and people cut across, the agents were cutting across and not really following the one-way system. So you needed to have strict enforcement. Limiting the total number of people in the store was effective at reducing exposure, but this was a big caveat that in our simulations, we were not looking at what happens outside. And in many cases, if you have people queuing right outside, inside a mall or some kind of shopping center, or just in a parking lot, that itself has lots of significant infection risks. So it's not as simple as saying, well, we've limited the total number of people, job done. There is a risk profile. You're just pushing the risk profile from within the store to just outside the store. Finally, the day of the week and time of the day was important, because during lockdown, we noticed significant differences in shopping patterns. The online shopping went up exponentially, but also the shopping patterns seen during the middle of the week was now being seen towards the weekend, and the weekend shopping patterns were now being seen during the week. And so this ability for us to then say, well, I'm running a simulation for Wednesday, but because now I know Wednesday is behaving a lot like Sunday, I can run that by saying pretend it's Sunday. I think I'm out of time now, so I'm going to stop.
Thank you very much, Sumanas, for your excellent presentation. Very interesting. I got one question from the attendees. The question is, supermarkets, including Sainsburys, often change products location, and people wander around in search of the product. Did you simulate that, and what was the conclusion?
Yes, so this is true. I mean, we did change the location of the products, but there were certain caveats around this. So maybe you want to change the location of the potatoes and the carrots, but the milk and because the refrigerated units have limitations to where you can move them. So we did try and simulate this, and again, it's hard to make a general sweeping statement saying, yes, yeah, you should move the milk to the front of to the store, or you need to move the bread, because everyone buys milk, bread, and eggs, and move those to the front of the store. The problem is that it's so specific to the store that what we found in some cases, it's better to have a channel that people are walking through, or maybe it's better to just have an open area.
Thank you. A second question, please answer it briefly. Do you have any idea about the number of secondary infections in Sainsbury?
So not really, because we weren't trying to model infections, as I mentioned. We were trying to limit exposure, because we realized that there are far more cleverer people looking at how the infections are being handled. Let them deal with it. We wanted to look at trying to reduce exposure as much as possible.
Thank you very much. Thank you. Thank you, Sumanas, for your excellent presentation and answer the questions within the 20 minutes. Thank you very much.
Thanks.